In the previous lesson, we were introduced to definite integrals. Now, in this lesson, we're going to continue to practice evaluating definite integrals. We're going to relate definite integrals to area. And then we're going to talk about the difference between total area and net area. In this first example, we're going to find an approximation of the area that's enclosed by the function and the x-axis over the interval from 1 to 6. So here's our function that we're using. It's a cubic. We have 0.3 x to the third minus 1.8 x squared plus 15. So in order to approximate this area, we need to use, according to the directions, we're going to use 4 subintervals with 4 rectangles. And so we need to first find the subintervals. We need to take the length of that interval from 1 to 6 and split it into 4 subintervals. Now, when we do that, we find the length between 1 and 6 by subtracting, and we get a length of 5. And then we need to find the width of each of those 4 subintervals that are equal by dividing by 4. So we could write that either by 5 divided by 4 or by 1.25. Now, to show the width of each rectangle, I created a number line so that you can visualize this. So we start with 1. And then we just keep adding 1.25 4 times so that we can see those subintervals. Here's the first one. So this is going to be the width of the first rectangle. This is going to be the width of the second rectangle, and so on. So these points where I have the gold dots above them, that's what we're going to use to plug into the function to find the heights. So let's take a look at what that would look like when we divide it into those 4 subintervals. So here's what it looks like. So we have each rectangle is lying on the x-axis over these subintervals. Now where the gold points are, that's what we're going to plug in to get our heights. So at 1, I'm going to plug in to the function 1, and then that will give me the height of the function. And then we just repeat that process for each of those rectangles. Then once we get the height of each of those rectangles, then we know what the width of each of those rectangles are. It's 1.25. So for the first rectangle, that's this one right here, we're going to take f of 1 and multiply it by the width, which is 5/4. That will give me the area of the first rectangle. Then I repeat that process for rectangle 2, but now I'm plugging in the point 2.25. That's this point right here that I'm plugging in to get the height of the second rectangle. And then I multiply it by 5/4, and that gives me the area of the second rectangle. So we just repeat that process until we find the area of all 4 rectangles. Then once we get all of the areas of those 4 rectangles, we can just add them up, and that gives us an approximate area that's bounded by the curve in the x-axis that will be about 43.93. So in example 1, we approximated the area under the curve using 4 rectangles, and then we got a value. If we had used, let's say, 5, 6, or 7 rectangles, the higher we go with the number of rectangles, we saw in the previous lesson that the more accurate that approximation is going to be. So now, instead of trying to approximate it with rectangles, we're going to actually use the definite integral to find the exact area under the curve. And remember that when we evaluate a definite integral, we are adding up infinite number of slices underneath that curve. So that's why it is accurate, so that we get the exact answer. So we're going to set up our integral using the same function we did in the previous example. We have 0.3x to the third minus 1.8x squared plus 15. And we're doing this over the interval from 1 to 6. When we find the antiderivative, we get 0.3x to the fourth over 4 minus 1.8x to the third over 3 plus 15x. And now we just need to evaluate it from 1 to 6. Remember that we plug in the higher value first, so our upper limit gets plugged into this first, and then we subtract that from when we plug in our lower limit. So when I plug in 6 to all of these terms, this is what we get. When I plug 6 in here, I get 97.2. When I plug in 6 here, I get minus 129.6, and then 6 in here would give me 90. Now we have to do that same thing. I subtract when I plug in 1 for all of these terms. So we're going to get 0.075 minus 0.6 plus 15. Don't forget that when you're subtracting the second evaluation for that lower limit, that subtraction applies to every term in that function if you have more than one term. So it's really important that you put parentheses around that to remind yourself that you have to distribute that negative. Now, the final answer that we get that's exact, once we work all that out, we get 43.125. So if we compare that to our previous answer, estimating with 4 rectangles, the estimate we got was 35.15. There's a fairly large difference between these two areas, but remember, we only used 4 rectangles, and there was a fairly big gap of missing area that we didn't count. Again, if I went up to use 10 rectangles or something higher than 4, this will get more and more accurate as we add more rectangles to our sum. In example 3, we're going to be looking at the difference between net area and total area. The net area is going to be when we find the area that's above the x-axis and we subtract the area below the x-axis. When you have an area that drops below the x-axis, that's considered a negative area, and that negative just tells us it falls below the x-axis. Anything that's above the x-axis is considered positive. So if we consider where it is above and below the x-axis and we use the signs appropriately, what we're going to get is the net area. That's going to tell us that if it comes out to be a positive number, that means there's more area above the x-axis than below. If it comes out to be a negative number, then that means there's more area below the x-axis than above. The total area is when we don't care about the signs. We don't care if it's above or below the x-axis. We just want to find the total of all the areas. So I would want to find this area. This area would just be positive. I don't care that it's below. I just want to find the amount of that area. And then A3 would be positive. So I would just add all those together. So looking at an example, I just made these numbers up for an example. Let's say the area A1 is equal to 2. Let's say the area A2 is equal to 5. And the area A3 is equal to 4. If I want to find the net area, that means we're going to take the signs into consideration. When I take the area of A1, that's above the x-axis, so that's going to be a positive. When I find A2, that's below the x-axis, so that's going to be a subtraction of 5. And then for A3, that area is 4, and that's above the x-axis, so that's going to be considered a positive. So when we evaluate this, we get 1. So this tells us that there's one more unit squared above the x-axis as below the x-axis. Now for the total area, we don't care if it's above or below. We literally just want to find the total of that geometric area. So here's where we just add all the areas together. And so the total area would be 11. Now, when you are using your definite integral to find areas, by default, this integral, the definite integral, will find the net area by default. It's just, that's how it calculates it. And then if you want to find the total area using a definite integral, you're going to have to split the integral into 3 separate integrals, because you don't want to take the signs into consideration. I'm going to find the area of this, and then because I know this is going to give me a negative area, I would negate it. So I would have a double negative and it would become a positive. And then I would just find the area of A3, and then I would add up all those values, and that would give me the total area. In example 4, we're going to find the value of the integral from 2 to 5 of the function x squared minus 5x plus 4. And we know that it's 2 to 5 because we have a lower limit of 2 and an upper limit of 5. So that means we're looking at this interval from 2 to 5. This definite integral symbolically represents finding the net area that's bounded by the x-axis and the function over that interval from 2 to 5. Now, if you notice from 2 to 4, this area that's bounded by the function and the x-axis is below the x-axis, which means this area is going to be considered negative when we're finding that net area. The area that's bounded by the x-axis and the function from 4 to 5 is above the x-axis, so that's going to be considered positive area. So we need to first find the antiderivative and then evaluate it from 2 to 5. When we find the antiderivative, we get x to the third over 3 minus 5x squared over 2 plus 4x. And we still need to evaluate it from 2 to 5. We first need to plug in 5. We always want to plug in this upper limit first. So when we plug in 5 into this antiderivative, we get 5 to the third over 3 minus 5 times 5 squared over 2 plus 4 times 5. And then we're going to subtract what we get when we plug in 2. Don't forget that all of these terms need to be negated because we're subtracting the entire antiderivative, not just one of those terms. So you have to remember to apply this minus to all of these terms. So it's a good idea until you get comfortable with this to always put parentheses around that second antiderivative evaluated at 2. Now, when we finish evaluating that, we're going to get negative 3/2, or as a decimal, it would be negative 1.5. And what this tells us is that there is 1.5 square units more below the x-axis than above it, because we have a negative here. So the example that we just completed, we found the net area. And you can think of it as, if the area is positive above the x-axis, think of that as a gain. And if it's below the x-axis, think of that as a loss. And so what you're doing when you're finding the net area, you're finding the effective gain or loss in the region between the function and the x-axis. Now we're going to look at the total area, and that refers to the combined area of above and below the x-axis, regardless of whether it's above or below. It's not going to take those signs into consideration. So we're going to use the same function so that we can compare the net and total area. So this is the same function, x squared minus 5x plus 4, and we're going to find the total area between 2 and 5. So this red area you want to think of as a loss. It's negative, it falls below the x-axis. And this blue area, that's above the x-axis, so that's going to be positive. So when we write our two integrals to find those areas, when I find the area of the red function, I want to make sure that I stick a negative in front of it because I know that this is negative and I want to negate the negative and make it positive. So I want to make sure that I can put a negative in front of that. Or another way you can look at it is you take the absolute value of that area. So we have the area in red. I'm trying to color code it here so you can follow along. The area in red is what's below the x-axis. So that's negative, but we want to make sure that it comes out positive, so we're going to negate it by sticking this extra negative in here. And that area goes from 2 to 4. So I'm going to set up my integral from 2 to 4. Now the blue area where it's considered positive, I don't have to worry about negating that because I know that that's already going to come out to be positive. When I add these two areas together, I'll get the total area that goes from 2 to 5. This goes to 2 to 4, and this integral goes from 4 to 5. So when I evaluate this integral right here, the first one, I get x to the third over 3 minus 5x squared over 2, and then this 4, the antiderivative will be 4x, and I want to carry down that negative because I want this to come out to be positive. And then I'm going to evaluate it from 2 to 4. For the positive area, I'm going to get the same thing for the antiderivative, but I don't have to worry about sticking a negative in front of it because I know that this is already positive. Now when I evaluate it, because I stuck this negative in front, when I evaluate from 2 to 4, I get 10/3. If I didn't put that negative in there, this would come out to a negative 2/3, and I'd end up finding the net area. Now, when I evaluate the integral from 4 to 5, I get 11 over 6. And then when I add the total area together, we get 31 over 6, and you can estimate that with a decimal as 5.17. So this is the total area. Now compare that to the area we found in the previous example, and you can see that the total area is bigger because we're not finding the difference between what's below and above the x-axis. All right, now let's sum up our lesson. The first big point that I want you to remember is that definite integrals help us find the area bounded between the function and the x-axis. The net area is when you find the area above the x-axis and subtract the area that's below the x-axis. When we evaluate a definite integral, that's going to give us the net area. And then the total area is finding the total geometric area without taking into consideration whether it falls below or above the x-axis.